So we're going to be looking at how epoxide can be open. In this video, we're going to be looking at the basic condition and specifically considering the regioselectivity of the reaction. Standard condition use, one example, sodium hydroxide and methanol, obviously basic condition. With these two, so we have the sodium and dihydroxide, so dihydroxide can grab the proton, deprotonate the methanol to form sodium methoxide and water. There's no big difference in pKa between the water and the methanol. Therefore, the position of the equilibrium will be dictated by the concentration bias. If you put sodium hydroxide in methanol, methanol is a solvent, the equilibrium will be shifted toward the bottom. And we're going to have, as the major nucleophile, that was the point of showing this, the methoxide. So the methoxide will be adding on the epoxide. Now that's where we can have two possibilities. We can have addition of the methoxide on this carbon here. I'm going to be showing that with a purple arrow and purple intermediate. Or the other possibility is the addition of the methoxide on the other carbon. So let's start with the purple one. So if the methoxide adds on this carbon, there will be cleavage of the carbon-oxygen bond, forming irreversibly, because the epoxide is highly strained, so we're going to be forming a structure. With OCH2. So on purpose, I didn't draw the stereochemistry. We're dealing here specifically with regioselectivity. The stereoselectivity will be discussed later. So what's important to show here is that the methoxide can attack on this carbon and break what was initially a carbon-oxygen bond to form an alkoxide. The other possibility goes with the methoxide adding on the other carbon. We're going to see that this is the most substituted carbon, cleaving the carbon-oxygen bond to give a similar intermediate, a regioisomer, where now the methyl group is at the same position. That doesn't change. The methoxide connects to this carbon, and we have the alkoxide on the other carbon with the cleavage that's shown with the green double bond of the carbon-oxygen bond. Following step, which is reversible, is the protonation of the alkoxide of both intermediate by the methanol. Methanol is the most important or highest concentration proton donor in solution. So we have protonation, cleavage of the hydrogen-oxygen bond, and that will form the two possible products, alcohol and methyl ether, and similar functional group here. I could say identical functional group, but at a different position, alcohol and methyl ether. What's the selectivity of the reaction? Which of the two intermediates is favored? It's important to know that because these steps are irreversible, once the intermediate is formed, it's committed to form the major product. So in this case, we have a good nucleophile adding on a neutral epoxide. So the good nucleophile will prefer to attack on the carbon that is the least substituted. So we have here a secondary carbon with the two alkyl groups, whereas this one here is a tertiary carbon. So the attack is easier on the secondary carbon. This is something you should have seen in Organic 1 in the form of a typical SN2 reaction. So that means that the major intermediate will be the intermediate with the methoxide adds here. That is this intermediate. I'll write major. And the other one will be a minor intermediate. Therefore, the major product is the product derived from the major intermediate. So that is the major product with the addition of the nucleophile in basic condition on the least substituted carbon because it's the most accessible carbon. And I can write here again that this is the minor product. Being under typical SN2 requirement, this reaction, so in basic condition, this reaction is called or is said to be under steric control. What does that mean? It's the size of the substituent or the number of substituent that dictates what is the major intermediate and eventually what is the major product.